Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at functions, and the goal is to try and better understand what sort of functions are, and then to move on to look at rules for transforming functions or graphs of functions and why they actually work. Full disclaimer at this stage, if this is the first time you're coming across functions, then the sort of content of this video might be a little bit too heavy. Even though functions are introduced in year one in the A-level syllabus, the content of this video is probably more suited to someone who's starting year two. I will make a video on functions which is more suited to someone who's seeing functions for the first time, but that's going to be on another day. Let's dive into the content of the video. So we begin with the definition of a function. A function is basically a mathematical machine which yields only one output for every input. So it's a machine, so it takes something in and it gives something out. And the important thing about it is if you feed it something, it's only going to throw out one thing. It's not going to throw out multiple outputs, okay? This might seem like a sort of a minuscule detail or something that's not that relevant. Actually, it happens to be a very profound aspect of the definition of a function. The other thing I should actually say is, more often than not, the cases that we'll encounter, the things that we're going to feed in are going to be numbers, and the function is going to do something to it, and then the thing we're going to have coming out are also going to be numbers. But functions can actually be a lot more complicated than that. The things that you can actually feed into certain functions need not be numbers, they can be other more exotic objects like vectors or even functions themselves, or lots of other crazy things, polynomials or shapes or whatever, and you can have really funky things coming out as well. So for this video, we're not going to discuss anything like that. We will just stick to the case of real sort of numbers going in and real numbers coming out. Okay, so let's just look at some basic examples of functions. So the way we write functions down, obviously, you'll be familiar with this, which is usually the inputs are called x and the outputs are called y, and the function itself is given some sort of a name, and f is very common. And so we have a function here which is called f of x, which means we put the input x and the output we get, we label it by calling it the function acting on the input to give us the entire output, which we say is f of x. And the rule here tells us how we actually get the output. So the function gets the output by basically adding 2 in this case, right? So the function adds 2 to each input to produce the output. So this is an example of a function. Obviously, another way of writing this is just to say we have an input here and we add 2 to it and we get an output. And as we've said before, if the input is x and the output is y, this is a perfectly valid way of describing what a function would look like. So of course, here's another example. The function need not just be called f. We can actually give it any symbol we want. So this function is called g, and the input is x, and the output is you take the input and you divide by 3. So the function divides each input by 3 to produce an output, right? So in red, we have our first example of something which is technically not a function, okay? So we have a process here, and the process is whatever you put in, we take the square root of it. And then we put a positive and negative because, you know, someone might argue that a square root doesn't just have to be positive, it can also be negative. That's okay, but the minute you define a rule like that, then the thing you have here is not really a function. Why is it not a function? Because imagine if you actually put 4 into the input. So you have x equals 4, you take the square root of 4, which we have here, and you actually end up with plus or minus 2. So you're putting in one number, but you're getting out two numbers. And that violates the fundamental aspect of a definition of a function, the fact that there should only really be one output. I must say that we have to sort of be very clear on the fact that all the inputs and all the outputs to a function must be well defined, okay? So this concept of things being well defined is very, very important in mathematics because we build concepts sort of in a hierarchy, one on top of the other, and if something is not well defined, then the entire thing seems to collapse. So what do I mean by inputs and outputs being well defined? Well, consider this example. So we have a function here, h of x, and what the function does is it just, whatever number you give it, so you give it x, it works out the output by dividing 1 by the number you've given it, right? So that seems nice enough until you decide you're going to give it x equals 0 as an input. Now the problem is 1 divided by 0 is mathematically not defined, and therefore the input x equals 0 into this function h of x cannot possibly be well defined. right? So the input is not well defined for x equals 0, and the output is not well defined for h of 0. So there can be other instances of where functions cause difficulty. So for example, if I come to the square root function, it makes no sense to put in negative numbers here, right? So if I put in -4 for x, that just makes no sense because in the real system, we can't take square root of negative numbers. So the fact that inputs and outputs must be well defined actually turn out to be quite important things. Indeed, this actually leads to sort of two key definitions, and the two key definitions are one is the definition of a domain, and the second one is the definition of a range. Okay, so the domain is actually a set of all well-defined inputs for a function. Okay, and a range is a set of all well-defined outputs of a function. So with any function, you should have a domain and you should have a range. Otherwise, we cannot be sure if the function is actually sensible and well-defined. Let's move on and consider a quick example of a function which is written clearly with its domain and range. So here we have a function, which is obviously, we get the function by squaring the inputs. The function is just y equals x squared. And the domain in this case, we could say all the real numbers between 0 and 10 as being inputs, where 0 and 10 are actually included. And the range in this case could actually be all the numbers that you will have come out, provided you've put in numbers only in the interval 0 to 10. And of course, you can sort of put those numbers in explicitly and then work out what you're going to get. And we'll get numbers which are going to be between 0 and 100. Okay? So let's think about why we actually need functions. So, why are functions actually important? There are two main answers that I'll actually give. The first one is they actually allow us to build ideas formally and rigorously, right? So an example of that would be the concept of addition itself, something so basic to mathematics that it's one of the first things kids are taught as part of counting itself. The concept of addition can actually be boiled down to sort of description of some sort of functions, right? And the second reason would be they actually allow us to study relationships between variables. And ultimately, that's the strength of mathematics, which is, it's a language in which we can describe relationships, which otherwise in English or in any other language we will actually have a very hard time to do. I mean, I personally don't even think it's possible to do. So examples of this sort of thing would be, so if x and y are related by some formula, say, then that formula can most commonly be just expressed in terms of some sort of a function. Okay, so for instance, you might have the relationship between force and distance. So you might have the force of gravity, and the force might actually be dependent on the distance. So this formula here could describe how the force is going to behave as the distance starts to change, right? So as the distance gets bigger, the force gets weaker. So you might have there might be some relationship between price of an item and time. So you can express that as a function, p as a function of t, and of course it will have some formula depending on exactly what item you're trying to describe. And indeed, people who are investment bankers actually spend a lot of time working on formulas where the goal is to try and find a function which will predict the value of, say, shares on the stock market at some time in the future. You can immediately see how functions are important in that context. Lastly, functions also allow us to describe positions or locations of objects over time. So an example might be, say, something moving in circular motion, right? You can sort of, if you do enough mechanics, you'll see that this sort of function is quite good at describing things moving in circular motion. So having seen what functions are and why they're important, let's think about how we actually go about studying them, right? So how do we study functions? Again, I'll give two answers here. The first way is actually using tables, okay? So since a function is simply a collection of inputs, in other words, the domain values, and the outputs, in other words, the range values, then to study a function, we just really have to study the set of sort of domain values and the set of range values, right? And we can do that by organizing them in some sort of a table. So I can have my inputs on one side and I can have my corresponding outputs on the other side. And we can then go away and basically study patterns in this sort of table of data, right? Unsurprisingly, because a lot of functions are going to have infinitely many inputs and therefore they're going to have infinitely many corresponding outputs, it's it's going to be rather awkward or even difficult actually to just study patterns in the behavior function by studying sets of numbers in some big table. So usually we want to actually turn to a graphical approach, right? So with a graphical approach, what we have is the information in the table may be actually converted into a form where we can visually see what the table is communicating in terms of the relationship between the input and the output. And how do we do that? So we do it by basically taking an input and taking its corresponding output and actually pairing them up and making a coordinate, okay? And we do that for each input and for each corresponding output. And then we end up with a collection of coordinates. So we manage to go from a huge table to just a huge list of points, and then we go to a coordinate system and we have inputs running on the horizontal axes usually, and we have outputs running on the vertical axes, and we go and we plot each point, and once we've plotted our various points, then the idea is to join up every adjacent point with every other adjacent point. And when we do that, we actually get some sort of a graph, which is basically a visual representation of all the information that would have been contained in the table in the first instance. Okay, the fact that each input has one output is clearly important here, right? So one reason for that is obviously the process of going from the table to getting the points will be a lot more awkward if that wasn't the case. And the second reason for that is when you actually come to plotting all those points and you come to joining them up, there will not be a unique adjacent point. So if I had a point here and a point here, but then there was also a point here, then how do I know which way to sort of do the joining up? So, the sort of things you'll have coming out are going to be a lot more awkward to try and sort of get one's head around. So I hope it's clear that we study functions usually by actually looking at their graphs, and in sort of some cases by maybe looking at their tables, but mostly by just looking at their graphs. Okay? We now turn our attention to a really important idea, which is the equality of two or more functions, okay? This is the sort of thing that actually should be present in most, if not all, A-level textbooks, but I'm usually disappointed in that when I look through them, this sort of thing is not there. So let's see what this definition actually says. It says two functions are the same, in other words, identical, if and only if they describe the exact same relationship, okay? So this really here is the criteria for when you know if I give you two different functions, in which case can you say they're actually the same function, in which case you can come back and say, no, they are very different functions, okay? So they're the same if they describe the same relationship. So let's just hear it put in a slightly different context, which is, so given a function y equals f of x, and given another function s equals g of t, we have that f is identical to g if and only if the table for each of the two functions for f and for g is actually exactly the same. So if you have two identical tables for two separate functions, then you know that those functions, regardless of how they've been written down, are actually identical, right? So perhaps it is worth saying the exact same thing in slightly different language, just to emphasize the point home, which is another way of saying the same thing is f and g are identical if and only if the domain of f and the domain of g are the same, and the range of f and the range of g are the same, and if f and g do the exact same thing to the inputs, okay, to produce their outputs. So in other words, you might have very different looking formulas in terms of symbols, but if they're describing the same relationship, it's actually the case that the two functions are exactly the same. So we have an example here. So we have y as our output, x is our input, f is our function, and in the second case we have s as our output, t as our input, and g as our function. But you see what's happening. The inputs are being squared to produce the outputs in the first case, and the inputs are being squared to produce the outputs in the second case. And lo and behold, the inputs in the first case are restricted to being between 0 and 10 inclusively. So that's our domain. and the inputs in the second case are restricted to being between 0 and 10 inclusively, and that's our domain. So in other words, we have the exact same relationship and we have the exact same domain, and you can sort of go away and check for yourself maybe that in fact the range for the first function is going to be exactly the same range for the second function, which means by the second sort of description we've given here, the two functions f and g are actually identical. So there is only really one function there, not two separate functions. And of course, you can also go away and actually construct tables for both f and for g for these inputs. And what you'll find is the two tables are going to be absolutely identical. So our two functions here, I'll repeat for the last time, are in fact identical. So before moving on to transformations, let's consider a summary of the key points we've actually seen so far. So the first one is functions actually describe relationships. The second point is every input to a function must actually have only one output. Okay. The third point is functions can be studied by basically looking at tables or by looking at graphs, right? And these are equivalent descriptions of functions in some sense. The fourth point is the order in which things actually appear in a table are actually irrelevant. Okay, I could go into this point a lot more, but I think it's probably useful if you go away and think about this in your own time as to why this is an important point, right? And lastly, the actual symbols or the actual names that we use to describe what the horizontal and vertical axes are on a coordinate system, or in fact what the input and output to a function is in terms of the actual symbols used to describe them, are actually completely irrelevant, right? The more important thing is it's what's the relationship between what's put in and what you get out. And this is precisely what I say here, right? Which is the algebraic relationship is actually the essence of a function, right? So the symbols used to denote a particular input or output of a function are actually completely irrelevant. So you've got a case here where you've got psi of mu and you've got mu being added 5 onto and then being squared, where mu is allowed to be any real number, and you've got h of x, where x is being added on 5 to and then squared, where x is allowed to be any sort of real number. Indeed, it doesn't really matter the fact that the output there is called, say, psi of mu, and the output here is called h of x, and the functions are written in sort of different symbolic language. The point is they're actually exactly the same functions. Okay, so these sort of subtle points, if they're not understood well enough, then when we start to do sort of more involved things with functions, people then start to struggle with them. So do make sure you really, really understand this point in red very, very clearly. So before moving on to transformations, let's quickly just focus on this remark, which is something that I've obviously already said, which is note that a function may have more exotic inputs and outputs, not just real numbers, right? Again, I want to emphasize this because as part of the A-level syllabus, we will see things like implicit functions, and we will see things like parametric functions. Okay, so if you're not sort of at least mentally and conceptually prepared for that, then when you see them, you might sort of struggle with them. So knowing that functions are actually a lot more general and a lot more abstract than just something which takes in real numbers and gives out real numbers actually helps one be prepared for what's to come their way. We will turn our attention to transformations of functions, okay? So the context I'm about to give here will hold true for all of the things that I'm going to talk about from this point onwards in the video. So we start off with a function. So suppose we're given some sort of a function, f of x, and this is a real function. So by a real function, I mean it's a nice function in that it only takes in real numbers and it only gives out real numbers, right? And we also assume that we're actually given the graph of this function already, okay? So we're given the graph of a function and we're given a function, and then we pick some real number, a, and we can actually go on to construct lots of new functions, right? So here are lots of examples of lots of functions that we can actually construct. So one way of constructing a new function would be to take the old function and to just add a number to the old output to be able to get the new output. Or you can take away a number to the old output to get the new output, right? Another way of constructing a function would be to take the old function and start to change the inputs that you're actually putting in by either adding a to the input before you put into the function or by taking away a into the input before you put into the function. A third way might be you get the output from your old function and you multiply it by a, right? Or you get the output of your old function and you divide it by a. So perhaps I should not have the 1 over a on the inside, I should actually have the 1 over a on the outside. So we have something like this. This is much better, which is, so let me just say it again. So here, we've already got our output, then we multiply by a, and that's our new output now overall. And in this case, we've got our output and we now divide by a, and this is now our overall output. And likewise, we can do the same thing, but we can actually fiddle with the things that are going into the function. So I can multiply my input by a before the function f acts on it, or I can divide my input by a before the function acts on it. And it shouldn't be too hard to understand that each time I transform my function f to get one of these functions, then what I actually have is I actually have a function in itself. So in other words, the old case was we have an input, then we have a function, then we have an output. But say in case one, we can just add a number and we've now got a new output. And what I'm saying is you can go from the input to a new output, and this thing here is actually itself a function, right? Why is it a function? Because f is a function, and so in the first case, we're only going to get one output for each input. But the point is, if I add a number to a given number, I'm only going to get one number coming out, right? So in fact, for each input, I actually only get one output, which means this thing here has to be a function. And here's the question. The question is, since we know the graph of y equals f of x, can we work out the graph of our new function, right? And the answer is we can certainly do that, and I will now move on to show you exactly how we do that. So the first transformation we're going to be looking at is actually here. We take our function f of x and we just add a to it, and this thing here is a new function, obviously, as we've already established, and I'm going to give it a name. I'm going to call it capital F of x, right? So the thing to keep in mind here is, since lowercase f of x is a generic function, I've not given a specific explicit formula for this, then we don't actually have an explicit formula for capital F of x. So when it comes to plotting capital F of x, we can't just put explicit numbers into the function and then get out explicit numbers and then plot them. So the only way we can actually plot this is actually by already knowing the graph of lowercase f of x and then being able to figure out some sort of a connection between lowercase f of x and uppercase f of x, okay? So one way forward is to figure out what will happen to a generic point, a general point, on the graph of the function y equals lowercase f of x as this transformation is carried out, right? If I can figure that out, then I know what the generic point on the graph of the function capital F of x is going to look like. So we seek the point x capital F of x, right? But since x does not have an explicit value, because we're considering a general point on a general function, so we have to be able to relate x capital F of x to x lowercase f of x, right? But we already have a relationship between the two because we know what the definition of capital F of x is. Then what we can basically say is x capital F of x is the same thing as x lowercase f of x plus a, right? And this basically tells me where the point would be, where the generic point would be for the function capital F of x. So let's take a look at that. So we see that since we are adding a to the y component, right, from our old point, so this point here is xy, but the new point we're getting for x capital F of x is just a more than the old point in the y component. So it's just going to be a shift up by amount a, right? And because that's happening at a general point, then really it's got to happen at every point on my initial curve, y equals lowercase f of x, and therefore if I go and do that at each point on my initial curve, I actually get my new curve, right? And so this is a generic point on my new curve, and this is the graph of my new curve. So in other words, when we actually have a transformation of the form where a is being just added to the outside of the function, then that's the same thing as the entire graph shifting up. And the way we describe that is we describe it using sort of a vector notation in some sense, and we put plus a in the second component, which is obviously the y component, telling us that we shift up by a. Just to sort of complete this, we can also say that actually if the transformation was take away a, rather than add a, then you will have a new function called g of x, and the same sort of reasoning that we've done here will go to show that actually the transformation will actually be a shift down by a, okay? And pretty much the entire reasoning is captured in that one line over here. So I'll leave you to sort of iron out the details of that yourself, and we can look at the next transformation. In this case, our transformation is doing something to the inside of the function lowercase f. So we define this to be our new function, uppercase f. And of course, the point is, because we don't have a formula for the lowercase f, we don't actually have a formula for the uppercase f. We do fortunately have a graph for lowercase f, so we can use that to work out the graph for the function uppercase f. So let's take a generic point, as we did last time, a general point, xy, and we want to work out the point x capital F of x. And if we figure that point out, we can plot it, and since that's a generic point, we can get the graph of the entire function, right? So last time we used the direct relationship, which was the definition of the function uppercase f of x. But in this case, that won't really help us much, okay? So we cannot plot capital F of x for our given choice of x. Why not? Imagine if we try to do that. So we've got x and uppercase f of x. Well, that's the same thing as x and lowercase f of x plus a. The point is there's no easy way to plot that coordinate. Why is there no easy way to plot that coordinate? Because if I come here and I say the horizontal coordinate for that point is the x value here, so that's completely fine, but the point is I want a height, the output, not for this input, I want the output for some other input, which is a to the right, but I don't explicitly know what that height is going to be because I don't exactly know what a is going to be, and we're taking a to be a general number, any real number, right? So this isn't really going to help us in being able to plot this point here. So what we have to do is we have to actually be quite clever. The most important part of the argument I'm making is as follows. We do not have control over this axis here. This axis here, the outputs are entirely controlled by our function. What we have control of is actually the inputs. Okay? And that's the key idea. So if we can go back and choose a suitable input for which we know that we're going to get an output, which we can basically predict, then that would allow us to be able to write down a generic point in a way where we can actually physically mark it with full confidence that it's the right sort of point on our graph. Okay, so here's what I'm going to say. So I'm going to say, don't take x to be the input, take x minus a to be the input. Okay, and now what? Watch what happens. So if I now go back to this definition and replace that x by x minus a, I've got to also replace that x by x minus a. So I actually end up with this. So I end up with capital F of x minus a is equal to lowercase f of x minus a plus a, because that's my input. The definition of f is the lowercase function f before evaluating actually adds a and then it evaluates. So when we do that, actually the negative a and the positive a cancel and I get f of x. So now consider this point here, x minus a, capital F of x minus a. And we know that's the exact same thing as x minus a to be our input, but our output is now lowercase f of x. Okay? So this tells us that what we're going to have is our generic point is such that actually if I was to put in x minus a, then the capital F of x minus a will actually give me the exact same output as the lowercase f would give me just at x, right? So in other words, the only thing that's going to change when we go from a generic point on our lowercase f to a generic point on our uppercase f is actually the x coordinates are going to go from being just x to being x minus a. So in other words, there's a shift to the left, right? Which is exactly what we have in this sort of vector description here. So the first component describes horizontal direction, and the negative would mean to the left, and the a would mean shift by a. So we see that we actually go from this point here as being a generic point on our curve to now this point here being a generic point on our curve. And if we do that shift by a to the left on all the various points on our initial curve, then we actually get a brand new curve, right? So we've been able to figure out the graph of our new function, capital F of x, from the graph of our old function. Indeed, I should add that we can actually repeat the entire argument that we've just done here for the case where we were taking away an a and not quite adding an a. And if we call that function to be g of x, then this argument here essentially explains as to what's going to happen. And in this case, we're going to get a transformation which is going to make everything move a units to the right. Okay? Naturally, the next transformation to consider would be multiplying by a on the outside. So we have a new definition for our function uppercase f of x, and I'm not going to go in as much detail as I've done in the last sort of two cases. So in this case, we again just want to plot x and uppercase f of x, but because that relationship is very simple, we basically just sort of use that relationship to say the uppercase f of x is just a lowercase f of x, and if our generic point was x f of x, which is obviously xy, on our graph for our function y equals f of x, so I'll just write that here. So since that was our generic point, then our new generic point is just basically going to be a times by the old y component, right? So that's the same thing as the y coordinate is now a times larger. So therefore, in this case, what we're going to have is we're going to have a transformation which is a stretch by scale factor a along the y-axis, right? The special case here obviously is if a happens to be 1, then there is no stretch because it's a stretch by scale factor 1, which means nothing actually changes. And if a happens to be negative, then some interesting thing happens. Obviously, there's still a stretch, but things are going to be a bit more funky. We'll consider an example of that case before we end the video. Let's take a look at the transformation where a happens to be on the inside. So our capital F of x is defined as f of a of x, where the f in this case is obviously lowercase. So we again want a generic point on our uppercase f function, on the graph of our uppercase f function, and we're going to use the relationship between lowercase f and uppercase f to be able to write that. So if we just write that out, the same question is now posed, which is, can we actually say where this point will be in relation to our general point? So if our general point is x lowercase f of x on our graph of lowercase f function, then can we actually say where this point is going to be in relation to sort of this point here? And the answer is, in this case, no. You can sort of draw a generic graph yourself and maybe convince yourself of this. The problem's going to be we know where the horizontal position is going to be of our coordinate. We're going to struggle to figure out where the vertical position is going to be on our coordinate for the same reason that I actually gave in the previous example. So what we actually do is we go back to our way of reasoning, which is we make a choice, a much better choice for our input. And the choice we make is 1 over a times by x. Okay, so when I make that choice, I put that into my function capital F of x, but then my function capital F of x is defined sort of very explicitly here, which is you take the lowercase f, you multiply whatever the input of capital F is by a, and then you evaluate the lowercase f. And when I do that, I see that the two a's are actually going to cancel. And so my general point on capital F of x is actually going to be x divided by a, and then the y coordinate is going to be just lowercase f of x. So in other words, if I compare this generic coordinate to that generic coordinate, I see that the y values are exactly the same. So the only things that's actually different is the horizontal component. And it's obvious that actually in the second case, the horizontal component is divided by a. In other words, it's been compressed by a, right? Another way of saying that is it's a stretch by scale factor 1 over a in the horizontal direction. Okay, so the transformation in this case works out to be a stretch in the horizontal direction by scale factor 1 over a. So let's take a look at two cases of reflection and then we can end this video. So the first case to consider is when f of x actually goes to negative f of x. So we define our capital F of x to just be the same thing as lowercase f of x, just with the sign of the output actually reversed. Okay, so we want a generic point on our capital F of x. We can start with our function of lowercase f of x, and we can look at a generic point on our graph of our function lowercase f of x. And since the relationship is so simple, I can just write down x capital F of x as the same thing as x negative lowercase f of x, and that's fairly straightforward. So I know how to be able to sort of plot this thing on the right hand side here from this point here, which basically means I can actually plot that point here. So I know how to plot this generic point, and of course all that happens is my y actually goes and becomes minus y, okay, which is the same thing as there's a reflection along the x-axis, because of course the x coordinate in this case and the x coordinate in that case is actually the same, right? So what we're going to have when we get a transformation which just puts a negative in front of the function we had, that is the same thing as actually having a reflection in the x-axis. So the second case would be we have a transformation where the negative is actually put on the inside of the function lowercase f of x. Okay, so our function capital F of x can be defined as lowercase f of x evaluated at not x, but evaluated at negative x, right? So again, we have our graph of lowercase f of x, and we have a generic point on the graph, so it's just x lowercase f of x, where y is lowercase f of x. And we actually want to figure out the graph of y equals capital F of x. So we need a generic point, x capital F of x. But using this relationship, we can sort of write this down. But again, it's the same point as we've always had whenever things are on the inside of the function, which is, okay, this is fine, but the problem is we cannot easily relate what this point is to what this point here is, right? So what we actually have to do is we have to pick a much more nicer input. So the output that we have coming out, we can actually relate to sort of this output here. That's really the key because we control the inputs in both these cases, but the function controls the output in both those cases, right? So what we're going to do is we're going to try negative x as our input. And when I take negative x as my input, then capital F of negative x is the same thing as lowercase f of negative x, right? That's just using the definition of capital F here. And when we do that, the two negatives are going to cancel, and I'm going to get f of x, which basically means that now I can relate my generic point here to this point here because the output in both those cases are exactly the same, and the only thing that changes is what's happening in the horizontal component, right? And we see that the x goes from being x to actually being negative x, and we can see that here. We go from being x to being negative x, and that's the same thing as some sort of a reflection along the y-axis, while the height of the 2 points that I actually have actually is going to be the same because the f value for both of them is indeed the same, and that's because of what we've actually shown here. I hope it's clear that if we were to do this for each point on this blue graph, right, where the y values are going to remain the same but the x values are going to swap and become negative, what we're actually going to have is we're actually going to have this green graph. So this green graph is a reflection of this blue graph about the y-axis, and this green graph is actually the graph of the function y equals capital f of x. So we've actually been able to figure this out, and with that I'd like to bring this video to an end. If you found the content of this video useful, then please hit the like and subscribe buttons. That's a great way for new people to sort of find this sort of content. And if you have any sort of topics on which you would like to see more videos, do say that in the comment section. As always, we will see you in the next video.